It's a great pleasure to introduce Kirill Magidson, who will be speaking about the Grothendieck-Lefschetz formula and the product formula. Okay, thank you.
I realized that there is a very good title. This book, like this, Grothendieck-Lefschetz. GL1 in there are two theorems which I will explain, which have the same abbreviation.
Shall we introduce?
Okay, so I want to recall first a little bit about the general strategy for proving a number. So this was explained very well in the talk of Behrend in the first talk. So the general strategy was that the Tamagawa number conjecture is equivalent to the following interesting product formula. So I have BunG X, the mass of BunG X divided by Q in GX, and this should be equal to the product of all points of the curve of the following. I have the mass of BunG small x divided by Q to the dimension. So here, BunG small x is just the classifying stack of the pi the group over a point. So I want to mention right away some assumptions will be assumed throughout the talk. So here G over X must have so smooth right. It has connected fibers and connected fiber is simple and simple connect. So this is just some assumptions that you have to impose in order for various aspects of this order to work, such as the existence of good certification of BunG of X, and also this conditions on generic semi-simpleness and simple connectedness are important for convergence of some kind of infinite products of the form which appear here. Okay, so so this is that assumption that I fixed throughout the talk, and so I want to recall also how what was the general plan of proving this formula. So I want to recall some classical story, counting points following real. Right, so assume phi over the Q is some quasi projective variety. And so if we're interested in computing the number of points, y over q. And there is a wonderful formula used in Grothendieck-Lefschetz, which computes this in terms of certain homological information. So let me denote y bar is the base change, y to the algebraic closure over q. And so this has this carries a arithmetic Frobenius isomorphism, which generates the Galois group of this extension, right? And in particular, the Frobenius acts on the étale homology of y bar QL conditions. Right, so theorem due to Wales that's attributed to Grothendieck-Lefschetz as well. So it says the following, that the number of points divided by q dimension can be computed as follows. So I take the sine sum, that's I h I of -1 to the I trace of the, so I have this Frobenius isomorphism is usually called arithmetic Frobenius, and the reverse of it is usually called geometric Frobenius. So here I have to take the pi inverse, and so it's x on hi well pi bar is QL coefficients. So this is just some higher dimensional vector space, and the Frobenius accident, you can compute the trace and the sine sum like this. And so this is an analog of Lefschetz's point formula.
And this was not compactly supported because it's the arithmetic.
Yes, so right, so it's factored here and factored the geometric Frobenius. So in this formulation, the homology is just the usual homology. Okay, so I want to introduce generalization. Media. So assume I have some b f so it will be an object that Bn. So just the vector space with an endomorphism. Vector space means the direct history, right? Full trace. Yeah. We use map on each homologies. Some are all. So this may not necessarily converge. Understand it formally, but so in the case it will be interesting, it will converge, but it will be it will take some work to actually show that it converges. Okay, so this is just a notation I want to introduce. Now, so I formulated this theorem for say quasi-projective varieties, where it's known, but it turns out that the similar formula holds for BunG, and in fact can prove the theorem by breaking it down into two separate statements. So one is theorem due to Kai Behrend, which says the following, that there is an equality mass of first divided by Q times the dimension of this type. Right, and on the other hand, I have the trace of geometric covariance acting on the stack, getting a homology of the stack, which are x distance. So see it just as so this is a complex of chiral vector spaces. It's not necessarily finite in any sense, but part of the claim is that this trace is well defined, and there is an equality. Yeah, the Grothendieck-Lefschetz formula holds for BunG on a smooth and proper curve over Q. Right. So this is one part of the proof. I think I can call it also GL1, Grothendieck-Lefschetz. And there is also theorem.
I get it. I see, that's an acronym, not a production group.
Huh?
I thought GL1 and GL2 referred to the groups.
No.
Oh my God.
Grothendieck-Lefschetz. Oh yeah, no, this is not Grothendieck-Lefschetz. This is Gaitsgory-Lurie.
Well, there's a 3, 4, 5 now.
Yeah, so Grothendieck-Lefschetz, sorry, Gaitsgory-Lurie says that on the other hand, there is the following, there is an equality like this. So on one hand, you compute the trace of geometric covariance on the étale homology. BunG X bar with field coefficients, right? And on the other hand, you have the right hand side of the statement you want to prove. Product. That divided by Q the BunG X. The product of all points, right? So we have two separate theorems. One of them is a very classical source. It's essentially Grothendieck-Lefschetz theorem for this particular stack. This was proven by Behrend. And then there is a completely different theorem by Gaitsgory-Lurie, which says that interestingly, this trace can be computed as a certain product like this. So these are two kind of very, very different theorems. The proofs are very different. And so the purpose of my talk hopefully is to mostly explain the proof, the strategy of the proof of this statement, and some crucial ingredient for this statement called the product form. Okay. So so let me begin with one. GL1 or G. And I want to begin with a certain form-up exercise. So here I want to prove Grothendieck-Lefschetz formula for some quite difficult stack. So one of the problems is it's not quasi-compact. So there are substantial issues with convergence here. But on the other hand, we also we don't yet know Grothendieck-Lefschetz holds for any stack at all. Like all we know is that it holds for quasi-projective varieties. And natural next step would be to try to prove it for sufficiently good arctic stacks. So section. So assume I is the smooth stack. I mentioned. And I have an action of smooth, fine, right on this step. Now, so I said the following that if Grothendieck-Lefschetz holds for phi, then it holds for phi modulo G. Okay, so let's try to prove it. Okay, so how do you prove it? So first, let's present homology. So there is a standard simplicial diagram computing this quotient. Right, so that phi, that's G, and then I times all other powers of G. One match here is projection, not is multiplication, and so that it continues to go. That is a standard simplicial diagram. And the étale cohomology of this quotient. Well, you can take the next thing as a definition, but I think it should be more clear how to define cohomology. So this is going to be the totalization. Phi, and then we can so now, so this is some cosimplicial diagram. And any cosimplicial diagram has a canonical skeletal, co-skeletal filtration. I don't know what exactly it's called. So give us a filtration on this thing. There is a filtration on Gucci, such that say some S credit piece of this filtration is going to be the homology of phi times homology of the group to the power S. And another way to say it is that when you just sum overall S, take the sort of associated objects, then it's given by the following: the tensor product, the homology of phi times the homology of the stack PG. Right. Okay, so there is a filtration on this thing. such that good looks like this. Now, the nice thing about trace is that it splits iterations. Namely, so say, so here I have a fitted logic and associated vectors. I can compute the trace of my inverse, let's see, étale homology. I have achieved bar, right? So this has a iteration with these associated vectors. But the trace is insensible to the successive extensions which arise in these filtrations. And modular certain convergence issues, you can believe that the trace is given by just the trace of the inverse acting on the good, and the good is given by each part tensor with h étale BG. Right now, so trace is also multiplicative. The trace of a tensor product is going to be the product of trace. So I can rewrite it as follows: inverse right now times trace inverse star type BG. Okay. So now we already know by assumption that the Grothendieck-Lefschetz formula holds for this type. Now, how do you compute this thing? So so here apparently there's the following equation, which sounds very natural, but the proof is actually not entirely trivial. Let's trace of which is the same as the following. I take trace of fingers h star cheaper, right? So this is not just an affine algebraic variety, and I keep the inverse. So let me say a few words about how to prove this statement, because it uses some idea which I think probably will appear in the top of that ever. Okay, so proof of the claim. So the proof of the claim is based on the following observation that so I have this homology of G bar, and this is an augmented algebra. This is an augmented algebra over QL over a field of characteristic 0, and it turns out that it's actually under these assumptions it's given by the free algebra on the following I squared, where I is augmentation of the deal of so this is some non-canonical isomorphism. In fact, it doesn't even matter if there is an isomorphism of commutative Q algebras like this. What matters is that there is a filtration on the left-hand side, such that associated rates look like this. And this filtration is just the filtration by the powers of the augmentation ideal. It's something that you can do in the commutative differential graded algebras over QL. Right? So this is on the other hand true for this thing. For BG, that it's true that it's given by also symmetric algebra, but on the sheet by minus 1. And now So let's say we want to compute the trace of an endomorphism. So yeah, one important thing is that the trace, so the Frobenius on this thing under this isomorphism is induced by the action of Frobenius on this thing. So in other words, you want to compute the trace of Frobenius acting on the symmetric algebra, and on each successive symmetric power, the action of F inverse is induced by the action on this thing. Now, there is a wonderful hypothesis in the theory of symmetric functions regarding how to compute the trace of an endomorphism acting on symmetric powers. So here it's not quite symmetric functions, like supersymmetric functions, because this thing can have both even and odd components. But if you think about the analogy with symmetric functions, the following statement might be believable. This is just exponent of the following series. So I take 1 over n and compute traces of f minus n, right? So f to the minus n means the nth power of f inverse acting on what? Acting on I modulo I squared by 1.
So then it is concentrated, right? Okay.
No, for BG, yes, because
For
this
BG,
thing,
yeah.
but for this thing not, right? Because
Right,
it's
right.
this is not, this is, yeah, so I think this is concentrated new integrals, but this is,
A lot of objects.
yeah, so I was saying like in
You were
general,
thinking about.
yeah, so for this particular thing, it is true, but for this one, no. But okay, so we have this endomorphism, the nth power of f inverse acting on this thing shifted by -1. But the trace of endomorphism acting on the shift is the same as trace of the same endomorphism, but now acting on my modulo I squared and times -1. Right? Okay, so I can write this as this, and then okay, then so I can write this as exponent of sum n with the 1 over base inverse squared, and then take inverse. Right. But in this sum, you can now recognize this is the same as computing the trace of Frobenius inverse acting on the symmetrical algebra. L modulo squared. That's the inverse. But now G is just an affine algebraic group. So for G bar we know the Grothendieck-Lefschetz theorem. So this is the same as G1 divided by G FU divided by Q times G. Right, so G divided by number of points of G over F. Okay, so we have this formula for the trace of geometric Frobenius acting on the étale homology of PG. And we also assume that we know the Grothendieck-Lefschetz for this stack I. So putting this all together, the trace of geometric Frobenius acting on homology. is given by the following. So I'm gonna have by Q divided by Q. This and divided by Q to the power Q T I minus G. Right? But this denominator is the same as the number of points in the stack G. Q. And this difference of dimensions is the same as the dimension of so the upshot is that we given some nice smooth natural stack for which the we already know that the Grothendieck-Lefschetz formula holds, and then smooth affine convection on the stacks. The Grothendieck-Lefschetz formula also holds for the quotient stacks. But now, of course, BunG is not at all a stack of such form. We cannot present it globally as a quotient of something nice by smooth affine convection. But the idea that we can use the harder Nelson-Hunt simplification.
Kirill?
Yeah.
Sorry, the formula, like number of FQ points of X divided by number of FQ points of G equals number of FQ points of X on G. You need something, some kind of like arithmetic hypothesis for that, right? Like every G orbit contains an FQ point or something like that.
I don't think so. I don't think so. I haven't. Oh, the way the theorem is formulated in Gaitsgory-Lurie is that yeah, we have a smooth acting stack and a smooth affine group action acting on it. So you Grothendieck-Lefschetz holds for the top stack and then holds for the quotient.
What was the example? We'd say X to be spec of okay, anyway.
Yeah, I do remember this one, Gaitsgory-Lurie. I don't think the one money could do. I think it's, I also remember it being a sort of like exercise in just formal. So basically, as you said, I just remember it being sort of.
Yeah, I don't see. No, I mean, there is something to prove here, right? It's not like it's a very natural statement, but it's something you. There is a little bit of an argument, but it's not. There are no conditions. I don't think there are any conditions.
Very nice argument.
So let's talk a little bit about the simplification of BunG. Mostly, we are going to recall certain things that Kai Behrend talked about last year, and I also talked to some extent. Idea stratify BunG by steps of form I over G such that Grothendieck-Lefschetz hold for all these heights. Right, and the simplification you use for this is the usual hardness in hand. So we are going to do two things. So first, we're going to decompose BunG as the disjoint union over all degrees. So I'm going to take the disjoint union over all elements in the whole classes. So I'm going to note it like this: X0 of G. And then I have G bundles of degree D. So there is a disjoint decomposition like this. So what Behrend proved was that the Grothendieck-Lefschetz formula holds for each of them. And then it takes some additional argument to prove that the sum of these things also converge to the right answer. So theorem Behrend. Grothendieck-Lefschetz holds for each BunG x BunG x. Right. I want to just say that, so small remark is that so Behrend proved the Grothendieck-Lefschetz formula for each of these stacks, right? Which is good, but it does not necessarily imply that it holds for the whole stack. But so it takes some additional argument, and I don't think it's actually in the paper of in Behrend thesis, but it should be somewhere between lines of the text of Gaitsgory-Lurie. So really what I'm going to prove is that what is outline the proof of the fact that Grothendieck-Lefschetz holds for each of these guys. And the sort of convergence of the sum of masses of all these guys to this thing is hopefully going to be something that Matt Emmert will explain to us. So let's work with BunG D for a little bit. So the problem here is again that even each of these disjoint components is still not quasi-compact and isn't a stack of finite type. So you have to stratify each of these guys further. So stratify BunG x. So presented as a disjoint union. Sorry, just increasing union. N greater or equal to 0. Stacks BunG dx less equal to 1. So what does the subscript mean? So P, let me give the following definition. So for P belonging to BunG x.
So sorry, just a quick reminder to self here. This stratification, this D stratification comes from basically the fact that every G torsor over X has a up to Weil group unique T reduction. But it's comparing it to the T stratification. Now you're doing a further refinement.
Yeah. Yeah.
Here.
Yeah. Yeah. So this is just position by degree. For any T here, like so there's an alternate degree of G bundle on X, right? So for any T, I can look at those which have a particular.
Oh, it's actually just the connected components is the same thing as I1 of G. Okay.
Yeah. I1 is like the coordinate of that.
Okay, so here so now this was a simplification decomposition of the disjoint union. Here it is going to be an increasing union of certain substacks. So first I give the following definition for bundle on X. The degree of instability denoted D I D is going to be the maximal over the following. So I take all parabolics inside the group of isomorphisms. And so for any parabolic, that is just the underlying vector bundle, the sheaf of Lianchus associated to this group. Right. So this is just a vector bundle on X, and I can compute this degree. So the degree of instability is just the maximal over all these numbers. Okay, so now So by definition, I say that some E belonging to BunG X is in BunG X less equal to 1, equal to n, if degree of instability P is less equal to n. So if you unwind the mean, for instance, for n equals 0, it just means semi-stable bundles, and then there is some concentration starting from that. Okay. So okay, so now we have the point position. Yeah, so each boundary that's equal to n is smooth. So that's clear because they an open subset of BunG. Smooth Artin stack of final type. And moreover, there exists and three markers. For n and some affine, small affine with action at n, such that BunG X plus 10 is equivalent to quotient. Right. So what's happening here is that first finite type is a good statement in particular it's quasi-compact as opposed to the whole thing. But also we can present it as a quotient of a Dirichlet stack by a small affine group action. And for stacks of this type, we can use the theorem I proved earlier today. So for Dirichlet stacks, proving Grothendieck-Lefschetz isn't difficult. Essentially, I think it boils down to the same theorem. And then again, so we have the quotient of a stack which we know Grothendieck-Lefschetz by a small affine group action. So it holds for the thing as well. Let me say just do you want to make break?
Up to you. You're in incredibly good time right now.
Yeah, so let me maybe do about 10 minutes. Then if you do like a few minutes break, you can
Back to the grind.
yeah. Okay, so yeah, so a few words about construction of again. So we are going to continue. We're going to study G bundles in the level structure. Yeah, so for G that X and that's the divisor. Split G D to be big stack. G bundles. And that's read the section. Without the section along it's called the level structure along D. So I have a G bundle on X and I can look back to my divisor and I want to have a section. So the claim is that you can find and so so there is particular this two. Yeah. Right, so the same conditions as here, but plus the level structure. Right, and this obviously gets to T G X plus equal to M. So so the claim is that choose T so that BunG plus equal to M. It's not the step. So this is claim one and claim two. So here I'm choosing some large enough T, but in general, you can show that this is this map. Let's call it F is a principal bundle with respect to a certain smooth algebraic group. For any capital T, F is a principal bundle. Again, I should have formulated the other way around. The second statement first, the first after it. Because the second statement doesn't really depend on T, right? In the first, we have to choose T such that the second is very much the second. So, so for two, we can just I can just tell you what gamma is. So it's going to be so I have T, X via some time, and I also have so so this rule is given by pulling back G from X to T, and then taking the other restriction like this. So this is always true. And now for one, you need to choose D, so that this twisted vector bundle, take the bundle P algebras corresponding to G, and I twist it by minus D. So I want to have not global sections. And the way it helps is that if you take any bundle with a T structure, with a level structure of D, right, you consider the automorphism group, and then this condition implies that the automorphism group has trivial tangent complex, and therefore the group of automorphisms of this bundle is non-effect. And this is the way you prove that this is the amount of that. So right. So this is the construction. This is the construction. And then this gives the proof of Grothendieck-Lefschetz for BunG GX less equal to M. Lefschetz are false. Equal to N. And then so we need to show convergence of its sum. So we determine the sum from the formula holds. Some traces. Geometric effects on homologies of this guy. So if you're right, there is no reason for it to converge, but a separate statement is that it does converge and both sides converge to the right thing. And this gives the Grothendieck-Lefschetz formula for the whole sheaf X. Okay, so maybe I'll talk about problem for the formula next hour. So now we can make a break. Okay, so I think it should take maybe another hour. Okay, so the poll. The other theorem sorry. The other theorem that we wanted to that we need to prove for the L conjecture finding for quantum that so you have this trace of Fabinho section and another knowledge of that's bar, right? Apparently it happens that this should be the intent product like this. Masses of BunG X equal X divided by 2 to the power of attention.
May I just ask a question to anyone who can answer? Is this only true if X is a curve? Like, is there no more general theorem about mapping stacks, products that replace points that will allow, I mean, because there's a sort of obvious way this you could imagine both sides to be generalized. But is this, I mean, obviously the proof is only going to work for curves, but is there any hope that it could be?
For run space, like run space, you only study like this finite subsets. But I think if you don't, if it's not the curve, you can go beyond region.
Right, it's no longer an E2.
You have a
It's bigger
surface
than
and
an E2
you have to
output back then.
take into account
It's terrible.
curves, etc. Now it's becoming more difficult.
So it's probably not true. That's our gas orders are certainly hard to prove, but
So probably maybe we have to generalize a little bit what you mean by these points, because this is essentially only separators of X being
Right.
one-dimensional. But if you
That's
don't have
X also buckwheat for it's complicated, but it's like not even classical and maybe
Yeah.
it's another year, but yeah.
no, I was just it's so compelling that both sides have like, you know,
Right.
maps from X into point BunG is clearly maps from each individual point.
Okay, so very interesting theorem. Let's try to unwind a little bit what the theorem means. So we notice that all the stacks that appear here are just classifying stacks of some affine algebraic groups over the case. And so for them, for BunG small x, what the Lefschetz formula holds. So each of the small holds is given by the trace of geometric equation section on the outcome. Right? Okay. So there are broken, right? The statement as follows. Case. First. BunG on the is the product overall points of traces of geometric linear acting on top homologies of this classifying sets. Right. But remember the trace is multiplicative. And assuming that what I will say it makes sense, assuming some convergence, etc. You can rewrite this as the trace of generated convenience acting on the infinite terms of this. Taking all point specs, right? And now we can ask the question, the following question. So what is the relation between L, GX, and infinite sense of codes? Right? So part of this question is you making sense of what this infinite product means. But sort of when you heuristically rewrite the statement like this, it seems very compelling that there is Frobenius, it could be a Frobenius equivariant equivalence between this thing and this thing, which applies an equivalence upon taking traces, and inequality upon taking traces. Okay, and so the precise statement of the relation between these two things will require us to go a little bit into the formalism of l-adic sheaves on prestacks, and it turns out that once the left-hand side is properly formulated, it turns out that these things are essentially equivalent, and this is the product formula. So, but to let me maybe outline the basic strategy, and then I will talk about l-adic sheaves on prestacks. So the strategy will be like this: we are going to construct certain direct sheaf on the non-space of X. The sheaves will be such that I have some point inside the non-space. I could point into a collection of points like this. Then, so B is going to be a sheaf in the sheaf sense, sheaf. So the sheaves look as a point of run like this, corresponding to direction points in the curve. Is just the tensor points like this of cochains on BG pull back to the next side. Efficiency in TL. And we have maps, have a map maps like this for any collection of points. XM, simply from the fact that if I have a collection of points in X and then G bundle on X, I can pull it back to this collection of points to obtain a number of principal bundles with respect to groups G and psi for all these points. Right, so there's a map like this, and this map induces a map of homology. So it's going to go like this. Well, I think this will start.
So sorry for a question then. When we talk about l-adic sheaves on rad space, here you've given us sort of fiber-wise or stock-wise maybe definition of what each sort of stock Schmick pullback is, what the Schmick fibers are. Is there a global way of describing what a sheaf?
No, I'm going to say.
Okay, I see.
Just outlining the strategy.
I'm sorry.
So that it will be clear what we are going to. So for any fine collection of points, for any points of the graph space, you have a map like this. And it turns out that you can do it factorially in all points of the graph space, so that the left-hand side can be integrated. So in the sense of chiral homology, which I will also define today. That will have to cohomology of yes, and so the theorem is that F is equivalence. And again, remember, G is has connected fibers, and the generic fiber is semi-simple simply connected. Without these conditions, saying is potentially not true. So these are those Lurie prove it assumptions. Okay, so so the goal is to B and so for that, let's talk a little bit about the general sort of formalism of l-adic sheaves. So let's begin with the case X is classic project. Say unit. So I have the left side. And the category of done sheaves for next. So there is some K-Lurie. So this is going to be contrast. That's actually to the whole done sheaves on X. Now inside this category we have the so maybe I should say here the sheaves X T to emphasize the benefits of the ring of equations. So now inside that I have the full subcategory of étale sheaves. Which is defined as follows. So an object F is in this full subcategory. F is an étale sheaf if the following condition holds. If for any F prime such that all étale homology groups of prime are zero, it follows that any map F is null. So this formulation is slightly different from the conventional formulation as in terms of gluing in the topology, but it turns out that it's not actually very far from the usual sheaf condition. More specifically, it applies the condition of being a sheaf in a topology and certain hypercompleteness conditions. So these are sheaves. And so the nice thing about the topology, so the following very nice facts. One is that so we have the inclusion sheaves into all two sheaves. So there's inclusion like this, and normally for some sheaf theories, this inclusion commutes with limits, but turns out here it also commutes with co-limits. Commutes with limits and co-limits. Moreover, attached sheaves on X is compactly generated. You remember Sasha, if you spoke, he mentioned that say just usual sheaves on say R1 is not at all compactly generated. But this here something nice happens in detailed topology. In fact, let me say what the description of compact objects is.
Sort of equivalence of one. Right? Sort of equivalent, two is sort of equivalent. Right?
Yeah, I think so.
Meeting with limits means that you have a left join, and meeting with elements means left join. So, yep.
But I think sheaf on a compact topological space is compactly generated. But I don't think there is necessarily a right choice. So much. Yeah, they're kind of very close to each other. Yeah, so description of compact objects. So definition F in sheaves is constructible if there is simplification X union X alpha. Now X alpha here is locally closed. So if there is simplification like this, such that F restricted, so this data X alpha is locally. It's the description of compact objects. Definition. Okay, compact objects is equivalent to the full case variable. Sheaves. Well, it's a compact generation, so that int data is.
You also need cohomologically bounded.
Right. Oh. Locally constant. Sorry. I think no, you're right. It was locally constant with
Final limiting cohomology.
defined range homologies. Find the many finite dimensional homologies. So I'm going to go to the zero penalties right away. So definition of X projective. l-adic sheaves, not at least sheaves L(x) is going to be inverse limit of following. I take sorry, let me get let's say compact objects. I'm going to say compact objects first. So I take the sheaves X l omega, then sheaves X z modulo L squared omega, etc. Right. There's an infinite tower of small infinity, small stable indicators like this. So I take this limit and then define sheaves l-adic. The large case as in but my attention is always just okay. So now regarding formulate, regarding touches. Reality. I assume I have a map X line. Projected. F. And this then gives a map on a type state as the type state is the other way around. So going to go the other way around. Specifically, if I have some u value of y like this, I'm going to take the power product. This is the value over x. Right, and so it gives the following duality of sheaves. Sheaves x, sheaves y. So first I have functor f log star, direct image, but the way you compute the direct image is that for any sheaf on x, so I'm going to construct a sheaf on y, right? So its variance object of the entire site is going to be same as the value of f on the file product. So I have a factor like this, and so it has a vector joint. That would be always true, but it also has a right joint. And this is thanks to this statement. Right, the joint F upper trig. So a couple of facts on these factors. So first, for any f next to y, f star reserves constructibles. And for proper y, f upper trig observes the whole units, or equivalently deserves constructibles. The statement is this is very formal. This is so I upper trig is a right joint. It might not be for limits. It might not preserve constructible objects. But for proper f from x to y, it does preserve colimits and compact objects. So these are the basic factors to know. Now, and so using for plurality of l-adic sheaves on quasi-projective schemes, we can define l-adic sheaves on any prestack. But let me just say in the case of
Sorry, it's slightly strange notation, right? Because like there's sort of always a functor that you would want to call f upper shriek, and it always preserves colimits. But what you're saying is like when f is proper, it's the right adjoint of f lower star, right? Like
oh, I think that f shriek always exists.
no, I mean the right adjoint of f lower star always exists, but I'm saying there's
You wouldn't call it f upper shriek?
I wouldn't call it f upper shriek unless f was proper, right?
Okay.
And you don't have that adjunction.
Yeah, maybe you're right. Well.
Also, when we, sorry, the actual question, so when we talk about constructability for an l-adic sheaf, is it that like when you reduce mod L to the n for any n, it's constructible? Because you kind of define constructibility.
Yeah.
Yeah, so it's,
But this I'm here just
you mean that it belongs in that, yeah. in the
Yeah,
first
so
case.
for any mod L for any mod L to the n for any n, it has to be constructible.
Right, and I guess the reason, so if we try to do something more naive, like just require that our l-adic sheaf was actually kind of locally concentrated stratification, that wouldn't allow for things that have kind of like infinite monodrome or something. Is that the idea, or like
Yeah, I guess.
what would be an example?
Oh, that I don't know. But no, they're definitely, yeah, they're definitely making correct definitions you can give. So some of this is the correct definition.
Sorry, I came up with maybe this was a little bit addressed, but I guess when you're defining l-adic sheaves like that, I think one categorically this would be okay, but my understanding was if we want to do some sort of infinity categorical definition of this sort, it would be much more subtle than just taking the limit, because I guess like if I take the limit, like in some sense I cannot define the derived category of l-adic sheaves this way. So does the subtlety somehow disappear when I'm working in infinity categories, like the subtlety that exists for derived categories, or
Well, for derived categories, you don't have a notion of context, right? So it's somehow if you work with any categories, is the correct
okay,
notion.
so I guess this
Yeah.
okay.
And it's in the homology category recovers the things that people construct in triangulated categories. I don't know methods, but
Okay, so I'm going to define the gadget called Lux sheaves on ground space, and I set as a category of six shriek sheaves on the ground space. Okay, so the definition goes like this. Remember, the ground space X is as a prestack, it's the colimit taking of all non-density of the category of all non-density finite sets as surjective maps of the schemes X to the T using diagonal maps. So using so for any subjective this, that is the diagonal inclusion, close comparing, and you take the colimit in prestacks, right? Okay, so now so in this situation, there is functor that. Right, and it's like a joint. And in this situation, both functions are continuous to preserve compact objects because the diagonal pairing is a proper map. Okay, so we have this equation, and now what we can do is we can take the limit of all categories of sheaves. On the whole non-empty sets and suggested maps of recently indicated using fullbacks. And another thing we can do is we can take what's called the max limit. So also using strict fullbacks. But the difference between max and strict limit is that in the first there are compatibility morphisms and their equivalences, but in the second thing they are not necessarily equivalences. So for instance, for F belonging to Lax sheaves X for them equals to T prime. There is a map. Those strict fullback. But this map might not be equivalence. And so equivalent may also this map is the same as this. And so we can as well think about the data of a large sheaf as the data of maps like this using push forwards rather than sheaf.
So if I just might ask the sort of big picture, the way to imagine this is you take some symmetric power of X and you imagine a sheaf, just a standard étale sheaf on that symmetric power of X, and then that sort of uniquely pulls it back to every higher surjection from every other finite set. Is it sort of
No, wait.
no, it's more complicated than that, so you can have some sort of chain. How would I think?
Yeah, it's like an inductive system. So like you could have, for example, the dualizing sheaf on non-space itself, its restriction to every x to the xt will be the dualizing sheaf of x to the t.
So maybe it's easier than to imagine it just what sheaves push forward. So that is something that pushes forward.
It's a compatible system, and it's like you can under the restrictions, like the upper map that he drew from ft prime to delta per sheaf of ft is an isomorphism.
I see, so it's not sort of determined at some finite level and then pulled back from there, it's something.
Or on the entire space, possible. Yeah.
Okay, that's good too. That's
Compact object will be supported.
I see, yeah, no, that's exactly the point I wanted to clarify, and kind of these things, because
Yeah.
my direction, my limits are not,
It's like an inductive system or something.
okay.
So the sheets is also category of output. Just impose the condition that all these maps are equivalences. That's it. Subcategory. But in general, we work in this larger category. And so indeed, an example of this would be we can consider the dualizing sheaves XT for all finite sets. Yeah, so maybe just small explanation that have a scheme, let's project the scheme of K, then the dualizing sheaf, and it should be shrink back of the constant sheaves the other step. Right, so and now I have this collection of objects, and they determine and shrink sheaf strict sheaf of the index. Okay, there's still quite a lot to talk about.
Not that is more.
Okay, so now one important notion is the notion of chiral homology of one sheaf on the front space. So assume that T for all T prime source is a Lux sheaf. On our X. Then theorems like this. So I can take F prime evaluated on X T prime. So F T prime is the sheaf on the this power. I can take global sections of this thing. So this is the same as taking the push poles of F T evaluated here, right? I'm sorry, evaluated on X T. And there is a map to T evaluated in X to T. Right. So here I'm taking global sections. So the map on global sections like this. So this is just a map of ZL functions. Right. So that compatible maps like this for any equals to right. So there are maps like this, and by definition, the chiral homology of F denoted like this. The integral of F over the round space, often sometimes just integral F. So this is the co-limit over T. That's the maps of all these types using the map segment structure here. So this is chiral homology, and
So when you take global sections, you take it in derived sense, I assume.
yeah, of course.
Which is like this notation looks like classical sections.
No, yes, let's of course derived sections here.
Nothing we do is classical.
Yeah, so a good example is when we compute chiral homology of the dualizing sheaf of the round space. Okay, so this is by definition the coordinate overall T omega T x to the T, right? So this is the coordinate overall finite sets and such maps of. So this global section is the same as homology. X to the T with coefficients in x to the T, right?
Oh. Yeah, so now just one question is, this co-limit, are we supposed to think? Maybe I'm classically, that's more, maybe this would. The way to think that is a compatible system of actual sections of the sheaves in general, or something, in some sort of derived sense or something.
Oh, it's a co-limit of complexes.
Okay, I see, so it's quite a lot of data, okay, but yeah.
Okay, so now what is this? But computing the homology with coefficients in the dualizing sheaf is the same as computing homology with coefficients in the constant sheaf. And so this is nothing but the homology of the round space. Now, I'm not sure if it was in the seminar yet, if it was mentioned in the seminar yet, but there's very theorem of Kirill-Magidson. I think everyone knows that the round space is homologically single. This homology is just equivalent to CL.
That's my job. Yeah.
So the chiral homology of this thing is just given by CL.
So I guess I would just quibble a little bit with you say homology with coefficients in the constant sheaf. I would argue that doesn't really make. It's still really homology with coefficients in the, like homology, like what people call the homology of the space, is like lower shriek to a point of the dualizing sheaf, right? So I think it still is proper to kind of write omega x to the t in there, because the point is like, because x to the t is proper, like lower shriek and lower star to a point are the same, but it's still the same sheaf that you're.
Right, what if I write it like this? Homology, this coefficient in CL.
Yeah, okay, I think there's only one way to interpret that, sure, yeah.
And homology of the colimit of this homology is homology of
Yeah.
the.
It's just that the constant sheaf is not actually involved, right? Like, and also like on Ron space itself, like the constant sheaf is not well defined.
Yeah.
Utilizing it.
And that ZL is thought of in the derived category or in the infinity category, mod ZL. Perfect, okay. It's actually complex, but
It's otherwise we just like.
There might be a little more than. Okay, so now I want to introduce the notation. So assume I goes to y is some map. So I is a free step. Y is called just scheme. So now, so I can define following object. It's going to be a sheaf on Y. Square brackets I Y. And the definitions are saying the fullback, start fullback, omega Y, then the push forward. So these functions, they make sense. They work for prestacks. First, I get a direct sheaf on Kai, then I push forward into Y. I don't know what the origin of this notation is. Perhaps there is some geometric intuition behind it.
What is f upper star when x is a prestack?
Well, so let's believe that it exists.
Well, it doesn't though, right? Because like, for example, if like x is Ron space and y is a point, then there's no upper star.
even for l-adic.
No, so you can say that this is
Yeah, because well, the way that you define l-adic sheaves on a prestack is shriek sheaves, right? So it's like an inverse system under shriek restrictions, so it's. So constant sheaf doesn't really make sense, right? Because it's not a compatible system under shriek restrictions, it's a compatible system under star restrictions.
I was thinking l-adic sheaf
so that would make sense for
On schemes.
schemes for stacks. No, you can say the following, that this is
It worked for like a art stackers. Not for like
you can say that. So you take the limit. Take the limit of all functions. Right. From the functions. Yeah, so if I think about my stack as in terms of the growth integration like this, right? So if I take any object, get to divide it into voids, or just get to divide it over schemes and take its image, I get just an affine scheme, right? So I can take this affine scheme and take this where for scheme. Next to y. By definition, x y is star over star omega. Okay, does it make sense now?
For map of schemes.
Yeah, for map schemes it makes sense, but in general, we take the limit over all such things for all affine schemes like this.
Like what, okay, if X is round space and Y is a point, like. For example, if X is round space and Y is a point, what is it?
Well, let's see. So if you take space. Well, so if you pull it back to any x to the t, I think you just get yeah, so if you pull back to any point of that space, just get the, well, let me maybe move to the sheaf B now, and we'll compute some sheaf stocks in the process. Okay, so okay, so sheaf. So first, going to define the stack run x. So this is the following stack. I have its say values on some stack R. It's going to be say f phi. So here f is a map of the stack x u and plus t. So no, so just saying. It goes like this. So you have NC to the spacing points, set of points of x over R, and E is G bundle on the following. So so a map like this is equivalent to an action points x set R, and so I want to have a G bundle of mu of t. Okay, so so there is a ghetto factor like this. And so for any okay. First, I'm going to define from x t as the following fiber. So I take x. I take the impact from x to the t. This projects to x to the t. And so for instance, it's even just a 1 point set, then run g x. 1 would be just the classifying effect of g, because it just the factor of points of the thing is going to be just point facts of R and each bundle. Okay, and there are so there are also maps like this for any T prime. So I have X T, I take the back over X to T to GX T prime. So now I define T to be the square brackets of GX T over X to T, where the map is the projection. Right. Okay. So and so for any prime, there are natural maps. This, which give box sheaf structure on the collection of these maps. The theorems of all elements and sets such as maps. Now, so to maybe partly answer the Justice's question, so let's compute an example of some strokes of this sheaf. So assume we have a geometric point from spec A to run X. And so this corresponds to a sheaf structure on X on this collection of things. So assume you have a map like this. This corresponds to a map from a client set like this. This is actually equivalent to a map from spec A to X to T. Now, so what is the sheaf slope with respect to eta or PT? So this is the same as near break B on T. So by definition, it's this. So what is this? It's the homology from G X T over X spec K. Now, this pullback is just the product of all BG mu of T, all T belonging to T. So I pull back it to all points like this. So this is going to be just as a product. Like this. Okay, so maybe 5 minutes. Okay, so now construction of the map. That's detailed. So you see, I constructed a sheaf on the last sheaf on the run space. Well, it turns out it's actually a strict sheaf, but even assuming that simply last sheaf, its stocks are just tens of products like this. So if I take the chiral homology of this thing, it kind of looks like the tensor product of this homology. So this classifying stacks of all points of the curved X. So this is kind of what I was promising before. So how do we construct this map? So consider the map from X times BunG X BunG X to the T. So what is this map? If I have a G bundle on X and a collection of points, then I can construct a G bundle on the divisor determined by this, right? And so this is functorial natural ET. And gives a map from DT to the following. Yeah, so this map is over X to the T as well. So, and this is just X yellow and the omega X to the T. So we have such maps for any T, which are natural in subjective maps. So the implication that we get a map on chiral homologies like this. So integrate view over the run space and map to homology BunG X GL and X to the T. So this expression taken over T. Now, so this is just constant in pi sets. It doesn't depend, right? That's what this does. But the chiral homology is determined for limit, and the tensor products commute with colimits in each variable. So we can just pull it out like this. And what we will have left is this thing, but as I explained by Behrend theorem, this is just 0. Okay, methods. Let's call it okay, so it's mapped from the chiral homology to the cohomology of BunG. So the theorem what is equivalence. And this somehow tells us how the homology BunG is computed in terms of the infinite tensor product of the homologies of all fibers of G for all points of X. Okay, so let's finish.
Any questions for the speaker? Right, let's thank the speaker one more time.